trap, which is the key component inside the memory cell. Older technology could only store 2 different levels of electrons. A lot of electrons or very few electrons, which were used to store a single bit as a 1 or 0. However, engineers have been developing more finely tuned capabilities for trapping and measuring different amounts of electrons or charges onto the charge trap. Most memory cells in 2020 can hold 8 different levels, but newer technology can have 16 different levels of electrons. This means that a single cell, instead of holding only 1 bit as a lot of electrons or no electrons, can now hold 3 or more bits. For this example, we're going to stick with 3 bits. So, in this cell, if we were to have very few electrons on it, it would be 1, 1, 1, while some electrons get designated as 1, 0, 0, and a lot of electrons are 0, 0, 0. There are 8 different levels for all the various amounts of electron charges that our charge trap can be set or written to. The key to the charge trap is that it is specially designed so that after it gets charged with electrons, it can hold onto those electrons for decades, which is how information is saved or written to the solid-state drive. I mean, it's called a charge trap for a reason. It traps electrons or charges for years on end. And in order to read the information, the electron charge level is measured, and the amount of charge on the charge trap is unchanged. However, in order to erase the contents of a memory cell, all the electron charges are forcibly removed from the charge trap, returning it to its lowest level, which is 1, 1, 1, and leaving no excess electron charges behind. Let's move on and explore how these memory cells are organized so that we can store more than 3 bits of information. After we zoom out a little, you can see that the memory cells are stacked vertically. This is where the vertical part in vertical NAND or VNAND comes from. This stack of memory cells, which is technically called a string, is composed of 10 charge trap flash cells layered one on top of another. When information is written to or read from a string, only one cell can be activated at any given time. And to do that, we use separate control gates attached to every layer in the string. It works like this. The bottom control gate first says, "Hey you, charge trap 1, what's your electron charge level at?" Then the bottom cell sends that information through the center of the string up to the information highway at the top, which is technically called a bit line. Then the next control gate for the second layer asks for the charge level in the second cell, and so on up the string, each cell sending their information up to the highway or bit line. The same kind of sequence happens when charges are being added to a charge trap, which is how information is written to a memory cell. The main thing is that only one layer in the string is either written to or read from at any given time. Let's move on in complexity. Next, we duplicate this string 32 times, and this gets us a page of strings. Let's review some terminology. This is a memory cell, and this is a string. And now here we have a page, and we're going to call this entire page of strings a row. When we duplicate the string, we also duplicate the bit line 32 times. However, rather than duplicate the control gates, we're going to have every cell in the same page share a common control gate. This makes it so that when information is written to or read from a row, an entire page composed of 32 adjacent cells, all in the same layer, are activated at the same time. Let's step up in complexity again. Next, we duplicate these rows 6 times until we get a block. But we're going to do it 12 times so we can see 2 blocks. Okay, so again, here we have a column. This stack of memory cells, here's a row, which is technically called a layer. And now, here's a cell, and here's a string. The second cell. Next, we have a page, a row, and finally, we have a page composed. We're going to connect the tops of each string in a column together so they all share the same bit line. And our bit line is looking like a highway now. Next, in addition, we have to add a control gate that selects between rows so that only one row is using the bit line at a time. These are called bit line selectors. As discussed, these bit lines are like highways, and the selectors at the top act as traffic lights that mediate the flow of information so that only a single row can use a block or is active. We're going to connect the top. Similarly, the control gates attached so they all share the same bit traffic lights for the layers, with bit line highways along the top. In addition, we have to add control gates along each layer. The solid-state drive can read from or write to a single page. These are called bit lines. Additionally, in order to connect to the bit line selectors and control gates, there are wires that drop down from above and run perpendicular to the bit line, so that only a single row can use. Let's quickly recap. 8 different levels of electrons are placed on the charge tracks in order to store 3 bits of information. These charge track flash memory cells are stacked into a string 10 cells tall, which are duplicated into pages of 32 strings in a row. Next, those pages are bit lines. Additionally, in order to connect to the bit line, and here we're showing 2 blocks. Doing some quick multiplication, we find that there are 3,840 memory cells, 8 capable of storing a total of 11 charge tracks in order to store 3 bits. With each pixel in our charge requiring 24 bits, our scheme is that we can store 410 cells tall, or this much of our overall 32 strings in a row. You need about 20,000 times the size of this layer in order to store the contents of this single page. And here we're showing where we learn about the actual size of the memory. All the principles we discussed remain the same, so keep those in mind. It's just that the size are much more expensive than we discussed in our example. It's hard to pin down exact numbers because manufacturers are continually improving their designs, and they're very